homework 17A due tomorrow. If you signed up for lab makeup time, don't forget to come in and do that. Help session tonight, as usual. I'll be working the exam problems unless there's nobody there that wants to see them. But I assume some people will want to see them so they can learn from their mistakes and maybe prepare. I haven't thought any at all since last time about what I'll do with the makeup problem. I'm leaning toward what I said, I guess, which would be one problem covering all three topics in moderation, and then you take that one problem and use that to replace something that you didn't do as well on in the first pass of the test. And you can still, of course, do the multiple choice for makeup credit at some point. I don't have a deadline in mind for that, it's just the further it goes, probably the less you remember. So I wouldn't put it off too terribly. Chapter 17, which we're maybe going to finish today, I think. That's my hope. There are a set of conceptual review questions for that, like there is most chapters, but we're not going to spend any time with those, so I would really recommend working on those at some point. And if you want to wait till it's exam time and study them, that's up to you, but there's enough confusion, I think, in general about the difference in electric field and electric potential and potential energy that it's just a good thing to work on some of those and try to clear up some of the issues you might have with it. And so that's these things called the conceptual review slides. We do those every now and then. I choose people's names, you know, try, but not to this time. Okay, well, we've of course been studying electrical energy. The big idea, I think, is that electrical, keep writing the symbol that we use in youth is infinite. And then there's the big idea, that there's electrical potential energy if you have two things. A charge to kind of feel the energy, and a voltage to kind of create the energy. I mean, those aren't exactly what happens. But in particular, there's two sets of things involved. There is the creation of the effect and the sensing of the effect. So two different types of charges involved. Just like the potential energy for gravity. Right? Potential energy for gravity is mgh. Well, where does this come from? This is mass related to big G. The little g comes from the fact that the Earth has mass. But this mass is different than that mass. You know, if I pick the eraser up in the air, which value do I plug in for little m here? The eraser or the Earth? The eraser. But if I didn't know what little g was, which value would I plug in over here? The Earth mass. So there are two masses involved. Same thing with electricity. There are two charges involved here. It's just that we're hiding one of them in the potential. Just like we hid the Earth's mass in little g. And then we've got two different types of potential that we've talked about. The potential due to a point charge and the potential due to parallel points. That's the only scenarios that we have or will cover. Okay? Now, last time we started talking about an actual device to store electrical energy. And in a circuit, that's called a capacitor. So here's a bit of a model of a capacitor. Two conductors separated from each other, and then they need to be able to be attached into a circuit. So I've brought some connecting wires just to pretend that, okay, that's got an attachment that could be put into the circuit. And so does this one. So there's a capacitor. It would store electrical energy by putting positive charge on one plate and negative charge on the other. That stores potential energy. Here's that same picture, except they're using rectangular plates instead of cylindrical plates. But it's the same idea. Now, they often don't come in big packages like that. What will happen is they'll put some sort of material in between them to keep them from touching, because it wouldn't be good if they touched, right? Since they're both conductors, if I let them touch, how many conductors do I have? Just one. And positive charge and negative charge are neutralized, and it wouldn't be storing any energy. So there's got to be something in between the plates to keep them from touching, and then you take them, and often it's rolled up. And it looks like it's in a cylindrical package, like this little green package here, for example. That's probably two plates with a material in between it that's been rolled up and then put in some sort of a package. I've brought a few capacitors. Here's a bigger one that I have. This one actually is even bigger yet in terms of its numbers. You can't even see them, but there's a bunch of capacitors in here. They just look kind of like the components you used in lab yesterday. They look a little bit like a diode or a resistor. They're just little cylindrical things with leads coming out the end of them. This is says NVIDIA, so I suppose this is a video card of some type. But you see there are some cylindrical pieces mounted on the circuit board here. Those are capacitors. If you were to take a circuit board and look at it with a bit of a magnifying glass, there are a lot of little components that are said to be surface mounted. They just lay right on the board. Well, on these boards, they'll be labeled C1, C2, C3, C4. That's capacitor number 1, number 2, number 3, number 4. So there's a whole bunch of capacitors in here. And then in memory chips, they're microscopic. You don't even see the individual capacitances. But this is just some examples of capacitors. These are all pretty big, just geometrically. Okay. So the capacitance of a capacitor is a measure of its electrical properties. You see for that. If I hooked up a battery between the red and the black wires, let's say a 10-volt battery, what would that do? Let's see. We have a little bit of circuit diagram now in that. So here's a 10-volt battery, let's say. We'll call that the 0 volts spot and the 10 volts spot. How am I connecting the battery up to the capacitor? Through a connecting wire. How does the potential change from one end of a connecting wire to another? That was something you did in lab yesterday. It doesn't. So if this spot is at 10 volts, and I use those alligator connecting wires to connect up to one plate of my capacitor, guess what? That spot is at 10 volts also. And if this spot is what we call 0 volts, same thing, use a connecting wire, 0 volts. So there's a potential difference between those two plates. But what's that mean? We created a potential difference back when we first started talking about energy. How did we do that? We piled a bunch of positive charges on one big parallel plane and a bunch of negative charges on the other. That's exactly what the battery does, is it puts a bunch of positive charge on that plate and the equivalent amount of negative charge on the other plate. And sure enough, that's got potential energy, because opposite charges attract. If those two were allowed to move together, they would, becoming kinetic energy instead. So I've got a voltage, 10 volts in this case. I've got a certain amount of charge then that showed up on the plates. Just take a wild guess as to what might happen if I made this voltage bigger. More charge. Okay? And it turns out that for many kinds of capacitors, the charge is directly proportional to the voltage. You double the voltage, you double the charge. Make the voltage 10 times bigger, 10 times as much charge. So there's a proportionality constant. That proportionality constant is called the capacitance. So C is the amount of charge stored divided by the voltage. C is the proportionality constant between Q and V. That's what capacitance tells you, is it tells you how much charge can you store for a certain voltage. Let's say you've got a few different capacitors. And one capacitor that if you, let's see, capacitor 1 stores 1 coulomb for a 10 volt battery. Capacitor 2 stores 2 coulombs when attached to a 10 volt battery. Which capacitor is bigger? 2. It stores more charge per volt. And that's what capacitance is. So many charges per volt. Capacitance is similar to heat capacity. Why is water a good coolant for a car radiator? Because it has a high heat capacity, which means you dump in lots of heat and the temperature doesn't change very much. It does some. Everything changes temperature when you dump heat into it. Same things here. For a big capacitor, I could dump in a lot of change without changing a lot of charge, without changing the voltage very much. So a big capacitor could store lots of charge per volt. The units here are coulombs per volt. How many coulombs per volt does this capacitor store? And those coulomb per volts have their own name. A coulomb per volt is called a farad, named in honor of Michael Faraday, who did a lot of electrostatics kinds of discoveries back in probably the 1800s. So let's get back to where we were here. Okay. There's our definition. C equals Q over V. Units are called farads. Circuit board capacitors, particularly the surface mount ones that I was talking, tiny capacitance, picofarads. Memory bits, remember in computer memory, actually each memory bit is a capacitor. They're in the order of femtofarads. That's probably not a prefix you use very often. Femto is 10 to the minus 15. So a bit of memory is 10 to the 15th, 10 to the minus 15th. So how much capacitance for a gigabyte? A gigabyte would be 8 billion bits, roughly. So about 8 billion femtofarads. 8 times 10 to the 9th times 10 to the minus 15th. 8 times 10 to the minus 6. 8 microfarads of capacitance to store 8 gigabits, which is a gigabyte. So it doesn't take a lot of capacitance when the electrical engineers have figured out how to store stuff in femto capacitance range. Okay. How do you charge a capacitor? Well, first of all, that's the word used to put charge on it. You charge a capacitor by hooking it up to a voltage source. Okay. And that voltage source then, because it is a source of constant voltage, as you learned about in electrical history too, then the voltage of the battery becomes the voltage of the capacitor. Notice that the Q that you use here is the Q on one or the other plate. And how much grand total charge is there? 0. So much positive and an equal amount of negative. So when you're quoting this formula, typically you use the amount of charge on the positive plate. So you put in a positive amount of charge, a positive voltage. Capacitance is a positive thing. So many farads, so many coulombs per volt. Turns out that there's another way to define that capacitance. Let's talk about our little C1 here. We've got 1 coulomb over 10 volts. This would be a 0.1 farad capacitor. Could I take that same capacitor and store 1 coulomb with 5 volts? Turns out I couldn't. A capacitor's capacitance is a property of the material it's made of itself. So I bought these demo capacitors for lab, and it says right on them, this is 100,000 microfarads. So it's 0.1 farad, so it's exactly this. This is a 0.1 farad capacitor. Notice it's not even hooked up to a battery. It doesn't have any charge stored on it. But it has a capacitance because it has the ability to store charge. But that capacitance is a result of its design. And then, here's a much smaller one, this little yellow one. It says that, let's see if I can focus my eyes on it here. This is supposed to be 500 nanofarads. Okay. Well, why is that? Why can't I just choose the charge and choose the voltage? Well, it goes back to this definition here that we played with when we first discussed energy. The more charge I put on this plate, the bigger the voltage difference is. It turns out that voltage and charge wind up, as we said here, being directly proportional to each other for a pair of parallel plates like that. So there is a number for the capacitance. Because the voltage, you double the voltage, you double the Q. So the ratio, you double this, you double this, that ratio stays constant. But there is another relationship for the capacitance. It's what I call the engineering definition. This is the electrical definition because it's based on electrical quantities. But for this same capacitance that we made here with a couple of big sheets of charge that were separated by some distance and had a certain amount of charge on them, so forth and so on. There's that definition. Epsilon naught, you know what that is. That's a number that you've been using, or at least something related to it. You use K most of the time. But you can look up epsilon naught in the book. A is the area of the plates, of either plate. So area of one plate, let's say. And D is the separation distance between the two plates. So a more accurate picture here would be to try to show these things as three-dimensional objects. So that they've got some area to them, just like this has some surface area. So does this one. And then how far apart are they? That's the letter D. So the area, the separation distance, and that electrical permittivity constant is called creative capacitance. Let's take an estimate of the capacitance of this thing for our two electrophorus electrodes. Well, let's see. Epsilon naught is about 8.85 times 10 to the minus 12. Okay. How far apart would you like me to hold them? How about, I don't know, I mean, there's a centimeter, maybe a millimeter? Let's assume that I could somehow hold these things a millimeter apart. It'd be pretty challenging. What would be easier to do would be to get a millimeter thickness of paper and just put between them. Then I don't have to sit here and try to, oh, paper, that's what I'm saying, that's just the same concept I just mentioned, right? We put something between the two capacitor plates. This yellow stuff or gold stuff over there. So let's say that's a millimeter. Let's just be really optimistic that we're really good and we can make something that small in between there. So there's D, 10 to the minus 3 meters. What's the area of one of these? Well, is it a square meter? Surely not. I mean, that'd be a yard square by a yard square. How many of these to make up a square meter? 10? 100? 10 in round numbers? Let's say it takes 10 of these to make a square meter. Okay. Then what's the area of one of them? 21. So, is this a big capacitance or a small capacitance? Incredibly small. Then we got 10 to the minus 12 times 0.1, that's 10 to the minus 13, divided by 10 to the minus 3, that makes about 10 to the minus 10. Tiny little capacitance. In other words, this doesn't hold very much charge per volt. how could I increase the capacity? I mean, this thing's 100,000, this is a tenth of a farad. And this was 10 to the minus, what did we say, 8, 7, 9 farads, something like that, 10 to the minus 10 farads. How do I get 10 to the 9th times more of these to put in this little package? Well, there's two things. Actually, there's three things. What could I change in this formula? There's three numbers. How to change the distance? Sure, move closer, but wow, you can't get them so close that they touch. There's some limit to that. What about the area? It would be kind of inconvenient to make these a square meter big, which would only make it 10 times more capacitance. But that is what's done often. There are clever materials to put in here. Usually it's something like activated charcoal, which has an enormous surface area because of all the little holes and pipe tubes, nanotubes and things running through it. So you can really increase the area a lot without making the package bigger. And then it turns out this number can change. This number is a property of the substance in between the plates. So air basically has this same number, but there are other chemicals you can put in between there that have a much different, a much bigger value of epsilon naught. And so, again, clever material scientists have come up with ways to do this. This is an entire farad right here. Whereas our two little plates was 10 to the minus 10 farads. So interesting. You couldn't imagine one of these when I was in your chair. Okay, and that's only been 40 years. A little more than that, but not much. I'm 63. So between 40 and 45 years ago, nobody even dreamed of having a capacitance of a farad. Just like that, that's just imaginary stuff. But such improvements in material science that now it's easy to go out and buy the things from Radio Shack or Best Buy or something like that.
So what's like an average capacitor in like a laptop?
Oh, it's going to be nanofarads probably.
Where would you need something?
Big amplifier systems, home theater system, kind of car stereo that you put in your trunk. You know, the speakers blow out the neighbor's windows when you turn on. Those amplifiers are going to have some really powerful capacitors, really big value capacitances. Probably not in consumer electronics kind of things, you know, your phone, your computer. I'm not going to have those kind of capacitances. Okay, let's see. We've talked about most of this stuff. Okay. We just talked about this stuff. I'm going to change this formula ever so slightly. Instead of changing that number, most of the time the equations leave that number the way it is, and they put another factor in front of it. That's the material factor. Depends on what material. For instance, if you have air, the factor is 1.0006, which means it's 1, unless you need 5 or 6 of the digits. But if you put quartz in there, it bumps it up by a factor of 4.3. If you put porcelain in there, it bumps it up by a factor of 6 or 8. Put strontium titanate in there, it bumps it up by a factor of 300. It's just more and more exotic materials will have much higher values of K, even than this. And this table's probably 15 years old. So it's great. We did this little calculation. What's the capacitance for a capacitor with 2 electrodes? So we've said that the idea is storing energy. How much wood does it, I've seen that sign up in the biology department, right? How much wood could a woodchuck chop? You've seen that one that they had written on the whiteboard?
Yeah.
Well, I've always thought it should be how much ground could a groundhog grind, if a groundhog could grind ground. Annie, how much charge can a capacitor store? That's where I was going with this. Instead of how much wood could a woodchuck chop? How much charge could a charge capacitor store if a capacitor couldn't store charge? Because you can't. Because that's the whole point of a capacitor, is to store electric charge. Well, I think I see a formula on the board that you would probably think, go write this down. If I've got a capacitor charged up to voltage V with with the amount of charge Q, how much energy would you guess could be stored by that capacitor? I wonder. You would probably think that. It turns out that's not correct. And I think hopefully I can justify that. Do you remember, this is just kind of a ancillary little conversation, but do you remember the potential energy stored in the spring? Remember that formula? 1/2 kx squared. Well, how do you store potential energy? By doing work. So how do you do work with a spring? You stretch it, and that work would be a force times the distance. So you might think that this is the force that it takes to stretch a spring times the distance as you stretch it. The distance you stretch it is x. You remember the equation for force, spring, Hooke's law? F equals, I heard it, K times X. Remember that? So using this simple idea, you think the potential energy would be kx squared. But it's 1/2 kx squared. Well, picture this if you will. I've got a spring attached here, and I'm going to store some energy in it. And the spring is relaxed. How big a force do I have to exert to pull it out a little bit? Not much. To pull it a little bit further, more, further, more, further, more, all the way out here took a big force. But it didn't take that big force the whole distance. The average force that I exerted is 1/2 the maximum force. So instead of a force of kx all the way out, it was a force of not much, a little more, a little more, a little more, and on the average, 1/2 kx was the force that I exerted. And that's where that formula, 1/2 kx squared, comes from. It's completely analogous here. The potential energy stored by a capacitor is 1/2 of QV. Now, with this equation, we can change the Q into CV. So this is also 1/2 times CV times V. Or we can change the V into Q over C, and it's also 1/2 Q squared over C. 3 completely equivalent formulas for the amount of energy stored in a capacitor. Well, which one do you use? Well, the one that maybe you have the numbers for already. For instance, let's see, here's an energy one, the defibrillator. How much capacitance for a defibrillator? If the capacitor is at 5,000 volts and supplies 1,200 joules of energy. So I know V is 5,000. Potential energy was 1,200 joules. If you wanted to calculate the capacitance for just those two numbers, which form for potential energy would you use? The one that's got potential energy and voltage, and then solve for C. How else could you do that problem? You could take this form and solve for Q, and then plug Q in and figure out C. I know you could work it around various ways. So just using the algebra. I've got 3 different varieties there. Here's an interesting question, I think. Where is the energy stored in a capacitor? Well, where is the energy stored gravitationally when I pick this thing up? You'd probably say in this thing, right? It's got potential energy, I let go of it, and that would have kinetic energy. Where's the energy stored when I stretch out my spring? It's probably in the spring. Where's the energy stored in a capacitor? Well, one obvious answer might be in the charge. Another obvious answer might be in the voltage, whatever that means. I'm not sure how to localize that and say it's stored in the voltage. I heard somebody else say something. In the space. Let's look at that for a minute. I want to show you an interesting little way of thinking about this. And the reason I do it is because it's so relevant to modern life, as it were. I'm going to define a new little quantity called the energy density. Which is the potential energy stored per unit volume. Just like mass density is mass per volume, so energy density, potential energy per volume. What volume am I going to use? Jason suggested the space. I probably should have pushed a little harder and said, what space? But you see that the capacitor kind of defines a volume with the two plates as the sides, and then the air, the space, whatever in between. So for that capacitor, the volume is the area of the plate times the separation distance. And now let's put in one of those potential energy formulas. I guess I really don't care which one we put in. So if I really believe that, I'd say you choose one. So tell me which formula. John, which formula? 1, 2, or 3? 2. 1/2 CV squared. Let's see if we can make some sense out of this. Well, there's 1/2. C could be written as, I'm going to pretend there's no material hanging around, so we'll get rid of that A for now. C could be written as epsilon naught A over D. There's my V squared. There's my A, there's my D. How's your compound fraction skills? The epsilon naught and the A are still in the numerator. The 2 and that D wind up in the denominator. And then there's an A and a D, and there's a V squared, and there's still a 1/2. Oh, I've got the 2. That's the 1/2. So what cancels? The 2 areas cancel. And then again, I'm going to turn that back into a 1/2. Epsilon naught, I got V squared over V squared. Let's go one more time back to this little model that we used to develop our potential energy ideas. And you see this idea that the voltage is related to the electric field and the distance. V equals E times X. Voltage is E times the distance, so let's change voltage to be E times the distance over the distance squared. Write it down one more time. 1/2 epsilon naught V squared. That might be one way to think about where the potential energy is stored, in the electric field itself. Ooh, that kind of gives electric field a little more importance than just a bunch of lines poking out from positive charges and poking into negative charges. At least if you believe that little derivation, it would seem to hint at you know how much energy is stored if you simply know the electric field. I got rid of all the geometry ideas. Well, let's see. Ever heard of energy being transferred by electricity? Let's see, there's all kinds of energy generating places down on the Ohio River. There's very big ones, you go to Kentucky, or 2 or 3 down there, and you see their smokestacks that go down if they're coal-fired or nuke-fired or what. But they make an awful lot of the energy, probably, that central Indiana uses. How do they get it here? Wires, electricity, electric fields. That's how much of our energy gets transferred. I don't know if you ever heard of John Prine. He was a folk singer back in the 70s maybe, and he wrote a song called Paradise. It was about him growing up in Kentucky and how they strip mined and ruined all the land and everything. And one of the key lines in that song was, Something about Paradise is gone because Mr. Peabody's coal train done hauled it away. Now, the Peabody Coal Company was the big coal mining company that did a lot of strip mining in Kentucky, and of course they take that coal and send it away, and people would burn coal, and that's how they generate their heat and so forth. So nowadays it doesn't take so much of Mr. Peabody's coal train. We get our energy often through electric fields. Here's kind of the hint as to why that works. I left my phone on the table upstairs, but how does your phone get signal? How does it know something's happening? How does your Wi-Fi work? All through electric fields. Energy can be stored. And if you can store energy, clever people have figured out how to store information. And so you can download web pages and get pretty colors and sounds and movie trailers and all kinds of stuff. Yeah.
Question.
Yes?
So 1/2 E naught times E squared. That's potential energy or is it energy density?
It's energy density. It's
And-
potential energy. Oh, so, thank you
Okay.
for correcting that
That
mistake.
makes sense.
Thank you very much. Yes, that's energy per unit volume. So many joules per cubic meter. Yeah, thank you very much. And I'm not going to ask you to do that derivation. I just think it's so interesting to see that you think about energy as being stored in fields. Of course, you think about energy as being stored in in chemical compounds and so forth. And ATP and ADP and mitochondria, you know, other ways of analyzing things. Here's a way a physics person might think about some energy storage. Well, nope, that was electrons. So, start, pick a problem. Let's talk about it. Other than 47, because we've already done that. 72 and 78 don't relate to capacitors, so I'll throw those out of the next two.
Okay, 39.
39, let's look at 39. How strong is the electric field between the plates of a capacitor? It's 0.80, what's that funny little symbol mean? Micro, which is 10 to the -6, or 0.80 times 10 to the -6 farads. That's my capacitance. 0.2 millimeters apart, or 2.0 times 10 to the -3 meters. What variable is that? I heard it. Little d is how far apart the plates are. Little d. What else do we know? Each has a charge of 72 microcoulombs. Let's do that. These things like this. There's our charge. I'm going to come up with E field. I would come up with E field over here. We had a connection between E field and the voltage. I do know how far apart things are, so how about if we explore that idea here? The potential difference is the E field times the gap. Well, I know that one, that's good. How am I going to get the voltage? Q equals CV, what's V? V is Q over C. And so now I know everything except the electric field. Typical units for electric field. You know what they are? You have to think about it. From this equation, what units would you have for electric field? Volts per meter. Okay, very common units for electric vehicles. The other we got from our Coulomb's law discussion, newtons per coulomb, force over charge. Not a set of units, it's a defined set of units. Okay? Let's talk about number 66. We won't get it finished, but there's just so much circuit analysis stuff and physics stuff in 66 that I think it would be good to talk through it. A capacitor of capacitance C1 carries a charge Q naught. Okay. How did it get that charge? That isn't part of the problem, I'm just asking. How did it get charged? How do you typically charge a capacitor? Hook it up to a battery. So somebody hooked up a battery to this capacitor initially, and it was a capacitance C1, and when it was all said and done, it said, oh, it's charged, it's got charge equal to Q0. So it's got a bunch of little pluses on one plate and a bunch of little minuses on the other plate. And now they disconnect it from the battery because the problem now starts here. A capacitor of capacitance C1 carries a charge Q0. So now we'll make it a little bigger, a little easier to see. And it's got connecting wires attached to it. Why don't the charges disappear? Where would they go? They're not connected. And the charge will just sit there. Why don't they jump from here to there? Actually, they can. That's the Van de Graaff. But you've got to get a huge voltage before it'll jump. And that's a good idea because otherwise the electric sockets would be awfully dangerous. The charge just jump from high voltage to low voltage all the time. Okay. Let me show you this little table right here. There's this property called the dielectric strength. Air about 3 million volts per meter. So here's a meter. If I had one hand at 0 volts and the other hand at 3 million volts, then lightning bolts would jump from one hand to the other. Air would turn into a conductor. Well, they didn't jump that far with the Van de Graaff, so I bet the Van de Graaff was not at 3 million volts. But they did jump this far. Van de Graaff was probably at 30,000 volts, 50,000 volts, something like that, because it was able to throw a lightning. It was able to turn a short distance of air into a conductor. And air conducts electricity if you push hard enough, right? That's one of, who's the guy's laws? Murphy's laws. If you push hard enough, it will give. Okay. Well, if you charge up something big enough, it will spark. Yes, sir?
So why, when something like arcs, why is it not a straight line? Why is it like
I imagine it has to do with the literal molecule-to-molecule construction of the air, that it isn't terribly uniform. Because it may be jumping from water to water, which is polar, as opposed to M2 to M2, which isn't very polar. That's my knee-jerk reaction. Must have something to do with composition of materials. Okay. So we've got this charge, we've got this capacitor charge. Like I said, we're not going to finish the problem, but let's talk a little more. It's connected to another capacitor, C2. Here's capacitor C2. And now they're connected. Okay, what do like charges do? They repel, and suddenly these positive charges have some other big conductor where they can go and spread out a bunch. So I think some of those charges wind up here and the same thing over here. Now, there was still no neutralization of charge. So how much total charge is there now? Q1, Q2. There's still that much charge. I just rearranged it. How did I rearrange it? Well, now we come to yesterday's lab. Pick a number for voltage right here. Let's say this is 20 volts. Here's connecting wires. What's the voltage right here? It's gotta be 20 volts. Because there's no potential change due to connecting wires, which is hopefully found in lab this year. Now, this is negative charge, we're calling that the 20 volt spot. Here's positive charge, make up a number for that voltage. That makes sense. It's gotta be bigger than 20. Because positive charge is higher potential than negative charge. Go back to some of our earlier pictures. So let's say that's a 60 volt spot. What's the potential right there? 60 volts. How does the voltage for capacitor number 1 compare to the voltage for capacitor number 2? Same thing. And now you've got two equations that you can use to solve and figure out what the final voltage is, what the final charges are, so forth. So the charge did not get consumed, and the voltage wound up being the same on both because they're connected. So that's a good problem to think through. So we're out of time. No, we're not. We've got a whole minute left. So let's get done in. So if you weren't here the other day, I got your exam. Come and get it. I'll talk through exams tonight. I want these back eventually, but you don't have to turn them back if you don't want to at this moment.